Okay, welcome to Math 158, Functions, Graphs, and Matrices. This is section 6.2, Solving Linear Programming Problems Graphically. If you've been going through this course, this is actually the last video in the course, so we're here at the end. And a lot of things that we've been doing this semester have kind of led us to the skills that we're going to use in this section, okay? What we're doing is called linear programming, and there's a lot of information here at the beginning of the page that may make sense now. It will hopefully make more sense if you come back and read this top of the page at the end of the video. We have a linear equation, and it's usually going to be in the form of z equals ax plus b, okay? Ax plus by. We call that an objective function. It's a value that we want to maximize, we want to minimize. For example, if you're in a business, you want to maximize your revenue, or you want to maximize your profit, you want to minimize your cost. Okay, and then we have what we call constraints, linear constraints, that are actually linear inequalities here. You'll notice cx plus dy is less than or equal to f, or cx plus dy is greater than or equal to f. Those values, those inequalities are similar to what we were doing in the previous video in section 6.1. If you've not seen that, go back and watch that video on graphing linear inequalities, where we're graphing regions as well. Okay, what we want to do is we want to explore, given these constraints, what is the maximum value that z can take on. Okay, they're optimization problems. We come up with an optimal solution. Okay, and there's some rules here for linear program that are fairly significant and informative. Okay, if the solution to a linear programming problem exists, it will occur at a corner point. That's the reason why in that section 6.1 video, and again, if you've not seen it, go back and watch it. And if you have seen it, recall that we graphed a feasible region. We graphed those inequality constraints. We came up with a feasible region, and I spent a little bit of time talking about how to find the corner points for that region. And basically what we're saying is that if there is a solution, if there is a value that will maximize the scenario or minimize the scenario, it's going to occur at a corner point, okay? If two adjacent corner points are optimal solutions, then all points on the line segment between those are also optimal solutions. That's the scenario I'm probably going to avoid in this video, but basically I'll point that out later, what it means if I have two corner points that are both equally optimal, equally beneficial, then all the points in between it would be fine, and there isn't necessarily one of those points better than another. Again, a lot of the regions that we're going to do here are going to be bounded like the regions that we did previously, meaning that perhaps my region might wind up being completely bounded, as opposed to a feasible region that may have constraints that look like this, and this, and this, and then this is our feasible region. And notice that there is no upward bound. That feasible region would not be bounded, okay? A bounded feasible region will always have an optimal solution. If it's unbounded, it may or may not have an optimal solution. And again, most of the problems we're going to explore in this section, in this video, at least as an introduction to linear programming, the regions will, for the most part, be bounded, okay? So let's look at example 1 here, which is pretty much just a generic case. I have these 4 linear inequalities, okay? Similar, again, to what was in section 6.1. So if I want to graph those, okay, let's get our axes here. So here's my x-axis. Here's my y-axis. Okay. Let's put some marks here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, I'm going to recall something before I go much farther. I don't really need to do my x and my y-axis like this, because if you notice, again, x and y are both greater than or equal to 0. So let's start over here. Because remember, what this means is we're only going to need the first quadrant. So here's my y-axis. Here's my x-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think that's good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do a little labeling again. 1, 2, 3, 4. It's good to have labels here. It's also imperative that you label points, identify those points, right? So let's graph this equation in blue. What I think I'm going to do there is I'm going to take negative 3x plus y equals 2. I'm going to add this 3x to both sides. Have a slope of 3 over 1. So we're going to go up 3, 1, 2, 3, and over 1. Okay, so here's the point 0, 2, and the point 5, 1. And let's draw the line that goes through those 2 points. Okay. Now again, let's test to see if the origin gets shaded. So if x is 0 and y is 0, those are both 0. 0 plus 0 is not greater than 2, so we're actually going to shade above this line. Recall that since x is greater than or equal to 0, we're going to shade to the right of the y-axis. Because y is greater than 0, we're going to shade above the x-axis, which the blue line pretty much takes out of play at this point. Now, let's graph this one in green. Notice that our x and y intercepts are both 0. If x is 0, they're both 10. If x is 0, y is 10. And if y is 0, x will equal 10. So let's draw the line that will go through those 2 points. And then test the origin, see if we shade toward the origin. If x and y are both 0, then 0 plus 0 is less than 10, so we are going to shade below the green line. And so we find that that little triangle is our feasible region. Okay, now we know that this point is a corner point, and that's the point 0, 2. This point here, which was 0, 10, is also a corner point. And then we want to find the other corner point of that feasible region, which is that point of intersection right there. I'm not going to assume that it's that point 5, 1. Okay, or 1, 5, I guess is really what it is. I mislabeled it. We're going to find that point of intersection between the green line and the blue line by solving the system negative 3x plus y equals 2 and x plus y equals 10. I'm going to choose to multiply the top equation by a negative 1. So the top equation becomes 3x plus y equals 2. And the bottom, minus y equals negative 2. X plus y equals 10. And so 4x, the y's will cancel, will equal 8. X equals 2. And notice that if x is 2, the y will equal 8 because x plus y is 10. So this is the point 2, 8. So my 3 corner points are 0, 10, 0, 2, and 2, 8. Now what we want to do is we want to maximize the value of z. So we're going to find 3 different z values. We're going to find the value of z for the point 0, 2. We're going to find z for the point 0, 10. And we're going to find z for the point 2, 8. And to do that, first we're going to put 0 in for x and 2 in for y. We're going to put 0 in for x and 10 in for y. And we're going to put 2 in for x and 8 for y. In other words, we took this point 0, 2, and substituted the 0 for x and the 2 for y. 0, 10, excuse me, we put the 0 for x and the 10 for y. For 2, 8, substituted 2 for the x and the 8 for the y. And now we're going to evaluate those. 6 times 0 is 0, plus 2 times 2 equals 4. 6 times 0 is 0, 2 times 10 is 20. 6 times 2 is 12, 2 times 8 is 16, and that is 28. Now we're going to look at the 4, the 2, and the 28. Which of those is the maximum? Because we want to maximize this objective equation. Okay, so we get a maximum of 28 at the point 2, 8. Okay, the maximum is 28, and that occurs at the point 2, 8. So that's what we do for a linear programming problem. Now, this problem has no application, it's just constraints. We've got a couple of examples here that I want to show you of linear programming problems and how this works. Now, let me shrink this just a little bit and show you that I actually have this entire page for one problem. I do have more problems, okay? So just keep that in mind. These might take a lot of space. A game company is developing 2 new games, a board game and a mechanical game. I'm going to let X represent the board game, and I'm going to let Y represent the mechanical game. Each board game requires a half an hour to manufacture, half an hour to assemble, and a half an hour to inspect and package. Each mechanical game also requires some time to manufacture, assemble, and to inspect and package, 1 hour to manufacture, half an hour to assemble, and a half an hour to inspect and package. Then notice that in a given week, there are 40 hours available for manufacturing, 32 hours for assembly, 18 hours for inspecting and packaging. How many of each, I skipped the sentence, that's okay. How many of each game? So I want to solve for X and I want to solve for Y. Here's how I'm going to set up my equations. It takes a half an hour to manufacture each board game. It takes a half an hour to assemble each board game, and it takes a quarter of an hour to inspect and package each board game. It also is going to take some time to assemble. I'm sorry. Okay, so let's look at number 2, right? So a game company is developing 2 new games, a board game and a mechanical game. I'm going to let X represent the number of board games. I'm going to let Y represent the number of mechanical games. Okay. Notice that we talked about the time it takes to manufacture, assemble, and inspect and package the board games. Manufacture, assemble, inspect, and package the mechanical games. We also have an equation for manufacturing, assembly, inspecting, and packaging. Okay. Now, each board game will take a half an hour to manufacture, half an hour to assemble, quarter of an hour to inspect and package. Also, each mechanical game will take 1 hour to manufacture, half of an hour to assemble, and half of an hour to inspect and package. Now, let me back up and say what I'm doing here. This is the number of board games. Y is the number of mechanical games. So for each board game, for each X, for each board game made, I'm going to spend a half an hour manufacturing the parts. For each Y, for each mechanical game I manufacture, I'm going to spend 1 hour manufacturing the parts. Also notice there's 40 hours available. So the amount of time spent manufacturing has got to be less than or equal to 40 hours. half an hour to assemble each board game, half an hour to assemble each mechanical game, and we have 32 hours, up to 32 hours available for assembly. Quarter of an hour to inspect and package each board game, half an hour to inspect and package each mechanical game, and we have a total of 18 hours available for inspecting and packaging. Okay. Now, the other reality here is that X, the number of board games, and Y, the number of mechanical games, must both be bigger than 0. You cannot manufacture fewer than 0 games. Okay. Now, one thing I am going to do here before I move on is I'm going to rewrite these, because I personally, at this point, would rather not work with the fractions. So before I go any farther, I'm going to multiply the top equation by 2, the second equation by 2, and the bottom equation by 4. And so what that's going to do is I'm going to now have my first three equations are x plus 2y is less than or equal to 80. X plus y is less than or equal to 32. And then x plus 2y is less than or equal to 36. X and y are both greater than or equal to 0. Okay, so now that we have these inequalities cleaned up, no fractions or whatever, now what we're going to do is we're going to make this a little bit smaller so I can see more of my page. We're going to draw our x and our y axes, and just like many of the problems we've done recently, we see that because x and y, whoops, I wrote x here, that should be a y, because x and y both have to be greater than 0, we only need the first quadrant. I also notice here that when y is 0, x is going to be 80. So I think I want to go by tens. 10, 20, 30, 40, 50, 60, 70, and 80. 10, 20, 30, 40, 50, 60, 70, 80. And you can kind of play with that scaling as to what you think you might want to do. So that first equation, okay, I could label it equation number 1. I'm going to use blue. If x is 0, y is 40. And if y is 0, x is going to be 80. Here's the blue line. Notice if x and y are both 0, 0 plus 0 would be less than 80. We are going to shade toward the origin. Remember that for both x is greater than or equal to 0, y is greater than or equal to 0. We're going to shade to the right of the y and above the x axis. So we're shading so far inside that little triangle. And then equation 1. Equation 2, I'm going to make it green, and I do label these like this sometimes, okay? Notice if x is 0, y will be 32, which is right about here. Let's label that. That's 0, 32. And if y is 0, x will also equal 32. So that would be 32, 0. So here's the green line. We're going to shade, again, if x and y are both 0, we're going to shade below it. There are times, this is one of the times where you'll notice that the green, the restriction on the green, completely eliminates the blue, and so we don't need to worry about all of that region there. Now, if x is 0, in equation 3, which I'm going to make purple, if x is 0, y is 18, so there's the point 0, 18. And if x is 0, y is equal to 36, which puts us about over here. There's our purple line, or our third line. Because I'm using colors, I probably don't need to label them 1, 2, and 3. I can refer to them as the blue line, the green line, and the purple line. But if I'm doing it all in pencil or all in the same color ink or whatever, I might want to label them. So now you notice that this region here is our feasible region. There are 4 corner points. There's the corner point here, which is 0, 0. That corner point there, which we labeled 0, 18. We've got this guy here, which was 32, 0. And then there's this corner point here. Notice that's where the green and purple line intersect, or lines 2 and 3. So to solve that, to find that corner point, I need to solve the system x plus y equals 32, and x plus 2y equals 36. I'm going to multiply the top equation by a negative. When I add those together, the x's will cancel out. They'll add up to 0. Negative y and 2y is y. Negative 32 and 36 is 4. Okay? And then if x plus y is 32, but y is 4, x will be 28. So that gives me this corner point here is 28, 4. So there's my feasible region, and there's my 4 corner points. What makes this now different, in addition to having a word problem that I get the equations out of, okay, we want to maximize the profit, right? So here, back here, suppose the profit on each board game is $10, and the profit on each mechanical game is $15. So my profit is $10 per board game plus $15 per mechanical game. Businesses are in business to make a profit. Okay, we won't get into arguing how much profit is okay or not, but that's something that they work for. How many of each game should be produced in order to maximize the profit? So what I'm going to do is take each of those 4 corner points. What's the profit if we make 0 board and 0 mechanical games? 10 times 0 plus 15 times 0 would be $0. If I made 0 board and 18 mechanical games, 10 times 0 plus 15 times 18 would be $270 profit. Notice I'm doing all 4 corner points. The profit for 28.4 would be 10 times 28 plus 15 times 4, should be 340, right? 10 times 28 plus 15 times 4 is 340. And then the profit for 32 board and 0 mechanical games is 10 times 32 plus 15 times 0 is $320. Now, it seems silly, and often I'm asked, do I really have to do the profit if I make 0? You really need to show what the profit would be for each of the critical points. Okay, for each of the corner points. You really need to check that out and demonstrate that. Now, notice that the maximum profit occurs $340. Okay. Now, the question is, how many board games should be produced each week in order to maximize the profit? 340 is the maximum profit that the company can make with these constraints. But the answer to the question is, they can make 28 board games and 4 mechanical games to maximize their profit of $340. I actually like to put all of that in my answer, so I'm covered either way. Okay, so there's a lot of work in one of these problems, which is why I'm only going to do a couple of examples here, but you do want to practice these. Okay, so let's look at number 4. Okay, suppose a small company produces 2 different models of kayaks. They produce a larger model, which I'm going to call X. So X is the larger model, and a smaller model I'm going to call Y. So Y is the smaller kayak. Okay. Same thing as the problem we did previously. The larger model requires 2 hours to manufacture, 2 hours to assemble, 3 hours to package, and so on. So I'm going to have one equation for manufacturing each of the kayaks, one equation for assembling each of the kayaks, and one equation for inspecting and packaging. Okay, so it takes 2 hours to manufacture each large kayak. It takes 2 hours to assemble. Whoops, that's on a Y. 2 hours to assemble each large kayak, and then 3 hours to package each large kayak. The small model requires 2 hours for manufacturing, 1 hour for assembly, 2 hours for packaging. The constraints we have here is the company has 120 hours, up to 120 hours for manufacturing, up to 80 hours available for assembly, and up to 132 hours for packaging. Okay? And again, X and Y must both be bigger than or equal to 0. So what that means is, since X and Y both need to be bigger than or equal to 0, recall, that I only need the first quadrant. Because X and Y must both be bigger than 0, so I know they're going to go to the right of the y-axis and above the x-axis, and that takes care of those two constraints. If I do a little visual inspection here of my equations, we can notice that we're going to need x and y intercepts up to, say, 80. So I'm going to do the same as we've done before and go 10, 20, 30, 40, 50, 60, 70, and 80. 10, 20, 30, 40, 50, 60, 70, 80. Put a little bit more detail in there. Now for the first equation, I'm going to label that blue. Notice if x is 0, y is 60. And if y is 0, x will also be 60. And so here's my first line, which I'm going to make blue. And get my ruler to turn there. Okay. And again, if x and y are equal to 0, we're going to shade below. In fact, if you check all three of those inequalities, you'll notice we're always going to shade below all three of them. For the second one, which I'm going to use green, if x is 0, y is 80. If y is 0, x will equal 40. So we'll graph that line. Okay, there we go. Didn't want to turn for a little bit. Oops, you'll see in a minute why I'm trying to be a little fussy here. Why does that keep snapping back? There we go. Sorry about that. And then the third line, let's use purple here. If x is 0, y is going to equal, excuse me, will equal 66. And if y is 0, x will be 132 divided by 3, which is 44. And so my purple line is going to go something like this. And can you see why we want to be careful? Because you'll notice that we have our feasible region here. We have a corner point at 0, 0. We have another corner point at 0, 60. This corner point down here is at 40, 0. But now notice that here, all three lines are not intersecting at the same place. So we've got to be very careful that we don't assume that they're all three intersecting at the same place. We have a corner point here where the blue and the purple intersect. We have another one here where the green and the purple intersect. So let's find the first one here where the blue and purple, that's the first and third line, are intersecting. So that's 2x plus 2y. Actually, I'm going to be more careful with my room here. So that's where 2x plus 2y equals 120 intersects with 3x plus 2y equals 132. And I can solve this by simply multiplying the top equation by a negative. So the negative 2x and 3x is 1x. The 2 y's cancel. Negative 120 and 132 is 12. So we have an x value of 12. 2x, I have to put the 12 in there. 2x, but x is 12, plus 2y is 120. So 24 plus 2y equals 120. 2y is 96. Y equals 48. So this point right here is the point 12, 48. To find the fifth corner point, that's notice where the green and purple intersect. So 2x plus y equals 80, and 3x plus 2y equals 132. In this case, I'm going to multiply the top equation by 2 and the bottom equation by a -1. So 4x plus 2y equals 80, and -3x minus 2y equals a -132. I hear you, I made a mistake, didn't I? That should be 160. 4x minus 3x is 1x. 2y minus 2y is 0. 160 minus 32 is 28. So the x value there is 28. So 2x, which is 28, plus y equals 80. 56 plus y equals 80, so y is 24. So this is the point 28, 24. Now our profit, notice, the company makes a profit of $75 for each of the larger models and $60 for each of the smaller models. So our profit equation is 75 for the large plus 60 for the small. So I want to find the profit for making 0 of each, the profit for making 0 large and 60 small, 12 large and 48 small, 28 large and 24 small, and 40 large and 0 small. And those are each my 5 corner points. Now recall that what we're going to do here, 75 times 0 plus 60 times 0, 75 times 0 plus 60 times 60. I'm just substituting the x value in for x and the y value for y in each of these equations. And then 75 times 40 plus 60 times 0. Now what I like to do to speed myself up here, rather than doing 75 times 0 plus 60 times 0, which I know is 0, you don't need to do this. But then 75 times 0, you're doing all 5 of these multiplications, which you can certainly do. Another option here would be in the calculator to go to Stat, Edit. This is where we went when we did linear regression in some of the previous videos. And I'm going to put in the x coordinates. And then I'm going to put in the corresponding y coordinates. And you'll notice that what we're going to wind up with is the series of ordered pairs with the x value in L1 and the y value in L2. Now I'm going to go to L3, press enter, and I'm going to say that I want to do 75 times the value that's in L1 plus 60 times the value that's in L2. And when I press enter, notice that all 5 multiplications are done at the same time. Okay, just another option on how to handle this. And then you'll notice that the maximum profit of $37.80 occurs when I sell 12 large and 48 small kayaks. To maximize my profit of $3,780. Okay? So there's a look at linear programming. I hope this makes sense. This is the last video of Math 158, so this is where we end. But make sure to take some time and do some practice problems and work on the linear programming.